We talked last time about regular expressions. So if we take the problem, the language L, and this language contains W such that W contains the substring, the 0, 0, 0. We actually go one level up, and we say, hey, does the string W, the string W, contain 0, 0, 0 as a substring? Well, this is a decision problem with the answer yes or no. Whenever the answer is yes, the string is in the set. And we wrote regular expressions last time. And one of the regular expressions, I think, does it contain 0, 0, 0? To list all of the W's that contain 0, 0, 0, we can take the string 0, 0, 0, and then append any binary string to the left or right of the string, and it should be good. So this is one way of representing the set. This is another way of representing the set. And the set, again, is just an answer yes or no. Today we'll talk about DFAs, deterministic finite automata, where you have a finite set of states Q. So this is your states. This set must be finite. So then, let's see, what else do you have? You have a transition function delta that says, so let's draw an arbitrary state Q. The state has no meaning right now. Then I have the character 0 and I have the character 1 in my alphabet. So we define a transition function, and we'll define this as Q2. We define a transition function that says, hey, if I'm in state Q1, and then I take the transition function. If I take the transition function, it means I consume one character of my input string starting from the left, 0. I end up in a state Q2. Okay, obviously we have our alphabet set, which is just in our case 0, 1. We have a start state, so where in this machine should I start? Well, if I started here, I wouldn't get anything. So we need to indicate which one of these states we're going to start at while executing a string on the machine. For any given string in a DFA, there should be a single execution path. So we define our start state by drawing an arrow to whichever state we actually want to start at. Then we'll have our set of accepting states. So let's say I made this an accepting state. I draw Q3 here. That means the string 0 is in the language, but the string 1 is not in the language. So we have a set of accepting states. This set of accepting states is a subset of the total number of states that I draw in this graph. And here it's just Q2. Let's say we call this DFA D. Then we write that the language accepted by this DFA is just the set containing the singular string 0. So this is just DFA basics. Now going back to the problem, do we contain the substring 0, 0, 0? These are the tools I have at my disposal. A finite number of sets, arrows to indicate transitions between sets. I must indicate a start state, and I can circle the states that end in accept after executing the entire string on the DFA. Going back here, actually, if we list strings that are in the language and not in the language, according to this DFA, so obviously the empty string is not in the language because if I don't execute anything, I'm not in an accepting state. We know for sure that the string 0 is in the language because I take the first transition function, end up in an accepting state. The string 0, 0, what happens? Well, I take a 0 and end up in an accepting state here. So I've consumed this 0. But the second 0 doesn't have a transition function defined. So what happens? Well, we say that 0, 0 is not accepted by the DFA. This is not accepted. Every year, someone screws this up on the midterm. We say it's not accepted because the DFA requires you to, even though I'm in an accepting state after consuming the first character of the string, and even though the transition function for 0 is not defined out of this, we say it's not accepted. In order for a DFA to accept a string, you need to traverse through the entire string once from left to right and end up in an accepting state that is well defined after consuming the entire string. So common mistakes people make. Questions about DFA basics? Yeah.
Is every state supposed to have all transitions?
You don't need to define every single transition. It's assumed that if there is no transition output, the string is not accepted. The alternative, think about this from an expressibility perspective. Let's say I don't define an output transition to every single state. How could I ensure that I reject the strings explicitly instead of having the person assume it? So let's say I don't have a transition going out from here, and I don't have a transition going out from here. Why is it not necessary from an expressibility perspective? In the sense that, what could I draw here that would tell the reader explicitly that I'm rejecting the strings?
It could be a failing.
Yeah, I could draw a failing state, F, like most of your grades in this class. No. And I could define every single output transition and explicitly put it in a fail state. So it's not really needed, but this not drawing any transitions is equivalent to this. Yeah.
So the only way to fail isn't just going through the entire string and not ending up at the accepting state. If you aren't able to go through the string, then it's also fail.
Yes, exactly. So if you're not able to go through the string, that means you end up in some, you've traversed only part of the string, and you're in the accepting state after, let's say, k characters. The k plus first character has a transition function that's not defined, which is equivalent to implicitly assuming that there's an arrow drawn from that k plus 1 state to a fail state. Common mistake people make. Okay, any other questions about the basics of DFAs or definitions? Cool. We want to draw a DFA for this. So let's think about this. Let's start with a drawing perspective instead of a formal set definition perspective. So I have some state. I need to start somewhere. So all I need to do is make sure I contain 0, 0, 0 as a substring. So the first character I read in the string, let's start here. This is not in the language. This is in the language. This one is also in the language. The first character I read is either a 0 or a 1. Essentially, what I'm trying to do here is count 3 consecutive zeros. So if the first character is a 1, this means this tells me nothing about the count of zeros on the string I've seen so far. So we'll go here. We'll call this our start state, and then we'll say q sub 0 means I have not seen. You don't need a semantic meaning for each state, but let's define it for our own sake. No zeros seen. Or we'll change this definition later. Okay, so I need to encounter 1, 0 now. So I go to Q1. Now, in Q1, so I've seen a 1 as my first character. No matter how many 1s I see as my first character, I stay here. I've seen my first 0 now. Well, the character after this could either be a 0 or a 1. So this is 0 or a 1. If the character is a 0, I'm making progress towards finding a substring 0, 0, 0, because I now have the substring 0, 0. So we'll put this as Q2. So that covers the case where the next character is a 0. If this next character is a 1, what does that tell us? So I'm here and I see a 1. That means I've seen a string like 0, 1, 1, 0, 1, which means if a substring of 0, 0, 0 were to exist, it cannot include this 0, and it's as good as starting over on a new string 0, 0, 0. So if I see 1, 0, 1, I know that this portion of the string doesn't contribute in any meaningful way to finding 3 consecutive zeros. So it's as good as restarting my machine here and saying I need to start searching for zeros again. So now I'm in this state. I encounter a 0. Same thing. So if I encounter, now I've seen the string 0, 0. So I've taken the execution path 0, 0. Now I see a 1. Same thing, I need to go back to the start and try searching again. And then, I see my third 0, 0, 0, 0. I end up in an accepting state. We'll call this ACC. And then I have to circle it to indicate that it's an accepting state. Okay, so technically, I don't need to define any transition function. I do need to define a transition function. Do I? Yeah, I do. Here's why. Let's say now I've satisfied the 0, 0, 0 constraint. So I have some arbitrary string, and I've seen 3 zeros. So I'm in this state now. If I see another character, if it's a 0, what's the behavior I accept? Accept or reject? Accept, because the substring hasn't gone anywhere, right? It's still in existence. So I know that if I see a 0, I should accept. Okay. What if I see a 1? Accept, because the substring hasn't gone anywhere. It still exists. So this should be, I think, a complete DFA, unless I screwed up, for languages where I see the substring 0, 0, 0. Does this make sense? So the construction process is, again, even with regular expressions, list strings in the language, not in the language. I would say go one character at a time and see, assuming the state of the previous characters, if I add this next character in, what is the behavior I expect? And make sure, he asked a question earlier about whether or not this needs to be defined. Careful, because if you do not define transition functions here, you may miss something that's still supposed to be accepted. So this is problem 1, I think. Even if it's not, close enough. Problem 2. Okay, let's take a look at the strings that contain the substring 0, 0, 0. Let's take a look at the complement of that language. So that is explicitly going to be the language where strings do not contain the substring 0, 0, 0. As a substring. Okay, so we have a DFA here that tells us when strings are in the language or not in the language. So we can try explicitly constructing this. Essentially, what would happen is anytime I see 0, 0, 0, I would need to go to a reject state. So let's take a look at this. We have a list of strings not in the language and in the language. So if we take the string 1, 0 here, we end up in state Q1, which is a rejecting state in this language, because I don't have the substring 0, 0, 0. But in this language, the complement of the previous language, where I should not contain 0, 0, 0. So actually, let's do this. I will refer to this language as L1, and I will refer to this language as L2. And we can define that L2 is the complement of L1. And I'm going to make a table where I have my string W. I have my language L1, whether or not it's accepted or rejected. What should I do? How about this? L1 accepts. And then we'll have L2 accept. Okay. So I have this table that I've drawn. So let's start tracing out the strings. So we take 1, 0. 1, 0 is not in the language that contains the substring 0, 0, 0. So I end up in state Q1. L1 rejects, but L2 accepts. Okay, I take the string 0, 1, 0, 0, 0, 1. I trace it out. 1, 0, 0, 0, 0, 0, 1. So L1 accepts, and I end up in ACC. And then, this accepts, but L2 should reject this string. Okay. So let's take one more example. 1, 0, 0, or 0, 0, 1. So I take 0, I take 0, I take 1, I end up in Q0. So L1 rejects. end up in Q0, but L2 should accept. Okay, so we start to see a pattern here. Does anyone see the pattern explicitly? I'll give you a hint that the pattern I'm looking for has to do with the accept state of L1. Exactly. So I'm looking for a pattern between the accept state of DFA1 for L1 and L2. Reject. So it turns out if any string, let's go back to meaning for a second. This is rejected by L1, this is rejected by L1, this is rejected by L1, and this is accepted by L1. That means that any string that is rejected by this DFA should be accepted by the DFA that I draw in L2. Anything that is accepted by this DFA should be rejected, unless I said the same thing twice, but you get the idea. So that means any state that ends in a rejecting state should be transformed into an accepting state here, and any state that is an accepting state here needs to be transformed into a rejecting state here. So I can draw the same diagram structurally. S0, no, S, Q0, Q1, Q2. Q2. Q, ACC. What did I do? I drew ones here. Zero, zero, zero. And no matter what I see here, so we'll rename this. So this is rejected, this is rejected, this is rejected in L. So in L complement, this should be accepted, this should be accepted, and this should be accepted. And then I'll call this Q final. This is accepted in L1, so the complement of the state should correspond to a rejecting state here that's not circled. Questions? Cool. By the way, DFAs represent regular languages. So regexes, or review real quick. Okay, regular languages are closed under, what are the three things? Complement, I think, is one of them. Never mind, let's not do this. Wait, no, this is fine. I know that regular languages are closed under complement. That's thing one. And then point two is I know that regular languages I know that regular expressions represent regular languages. And I know that DFAs represent regular languages. So in your head, the idea the language is regular should be mapped to the idea that I can create a regular expression for this, and I can create a DFA for this. If I can create a DFA, I can make a regex. So language is regular equals DFA exists equals regex exists. So we can actually prove, now, or confirm regular languages are closed under complement. Let's say we didn't know this property about regular languages, that they're closed under complement, but we knew that DFAs could represent regular languages. Then we could draw, for any arbitrary DFA, we could switch the accepting and rejecting states, and we've created the complement of the language that it should accept, which proves that regular languages are closed under complement. Does that make sense? Cool. Okay. Is the pace okay? Cool. Okay, let's say, by the way, I'm not following exactly the lab. I'm just trying to get a variety of DFA questions in. Let's say I want DFA, I want to represent the language L such that, we'll call it L3, This is a set of all strings W such that 0, 0 belongs to W and not belongs to W. 0, 0 is a substring of W and 1, 1 is a substring. Okay. So why is this language regular? We can start by thinking about, I need to contain both of the substrings. So to contain the substring 0, 0, let's start by confirming that this is actually regular by making a regular expression. So if I did this language, this has 0, 0 as a substring, but not 1, 1. If I did this, this has 1, 1, but not 0, 0. So I know that this is a regular language. By the way, this is also good material to know. This is L sub A, or L sub 0, 0. This is L sub 1, 1. So if I were to ask you to prove on an exam maybe, instead of drawing a DFA, prove that L3 is regular, I wonder where something like this might show up. If I ask you to prove it, you don't need to draw a huge DFA or come up with a long regular expression. What we know is we can say L00 is regular. Why? Because I can write a regular expression for it. So L00, hence I can write a regular expression, so it's regular. I can say L11 equals, because I can write a regular expression for it, it's regular. Then what property of regular languages can I use to show that L3 is regular? Union, close. So the reason why union may not work is that would mean I have either 0, 0 as a substring or 1, 1 as a substring, but I need to enforce that both are substrings. So not union, but concatenation would mean that I have 0, 0 first and then 1, 1 after. Or I would have 1, 1 first and 0, 0 after. So you could write out both of those explicitly and say, I could say that L3 is equal to L00, L11, union with L11, L00, I guess. This should work, right? But there's an even simpler way of doing this. Intersection, right? So now I can say, okay, L00 is regular because I can write a regex. L11 is regular because I can write a regex. That means L3 is the intersection of these two things. And this is a regular language, this is a regular language. Hence, the intersection of two regular languages is also regular, so L3 is regular. Obviously, use more words than what I did. If we take this approach, and we wanted to actually write a regex for L3, so I will erase this for now. Well, I know I need to have the substring 0, 0 and the substring 1, 1. Let's say I fix those two things in. Okay, if I need to contain both substrings, either the 0, 0 needs to come before the 1, 1, or the 1, 1 comes before the 0, 0. Right? Then I can put any binary string that I want, plus which is exactly the same thing as the union idea you suggested. So many ways of proving that languages are regular. Or you could also draw a DFA for this language to prove it's regular. So let's try to do that. So DFA for L3. So I want to prove it's regular, I draw a DFA for L3. Okay. So we run into an interesting caveat here. Let's take the string 0, 0, and then 1, 1. Let's draw a DFA for 0, 0, which is going to be something like 0, 0 as a substring, 1, 0, 2 zeros, Also check my DFAs. I could be making mistakes. This is just for L00. 1. Does this look right for L00? Ooh, oh yeah. Yeah. Cool. Now does it look right? Yeah? If not, I guess you learn it wrong. So L11, only 1 is a substring. So same idea, 1 is a substring. I end up in an accepting state here, no matter what I see after. Q0, I don't know, we can call it QA, QB, QC. Okay. And then everything else, zeros should go back. Does this look right? Yeah? No? There's a loop. Thank you. With the value of 0, right? Does this look okay? Okay, so now I want to know if an arbitrary string falls in the language. So I first execute on this thing. I'll put this here. And okay, L00. So I go to 1, 0. I see a 1, I go back. I see another 1, I stay here. I see 2 zeros, and I end up in an accepting state. So I first simulated this on machine D00. So first run W on L00. I get a yes. Next, well, it should be the DFA for language 00. Next, I run W on L11. And so I get 0, I get 1, 1, and then I stay in the accepting state. So this tells me this DFA accepts, so I know I'm regular. This would be another proof to show that it's regular. So multiple ways of proving it. Write a regex for each, take the intersection, draw DFAs for both, and say, because I drew 2 DFAs, this is regular, intersection of 2 languages. Many, many ways of proving this. Okay, so the problem, I think, asks us, draw a DFA for L3. The issue with the approach I've drawn here, not for proving, but for coming up with a DFA, is I can only consume my input string once. So right? So let's say, I don't know, I drew like a 0, 1 here and tried to merge the 2 DFAs together. Well, I'm only allowed to consume my input string 1 time. If I were to choose one of these 2 machines to run the input on, I would consume the entire input here. And then if I were to choose this machine to run the input on, I would consume the entire string here. Do you see the issue? I'm only allowed to run my input string once through the DFA if I'm making a singular DFA for L3. Okay, so ideas. Let's say I only consume my input string once. What if I ran somehow a parallel execution of the string on both machines? So I take 0 here, I end up in this state. I take a 0 here, I end up in this state. I take a 1 here, I end up in this state. I take the same 1 in parallel here, end up in this state. I take another 1 in parallel, end up here, take another 1 in parallel, end up back here. I take a 0. Currently, my state is now here. And if I were to parallelly execute a 0 here, I would be... Actually, I don't know where I'd be. Where? Yeah, thank you. I already accepted. Cool. So now I ran now last 0. 1 more 0, I end up in an accepting state here. I'm parallelly executing it on this machine, and I end up in QC again. So at the end of my parallel execution, both of them are in accepting states. Okay. So how do I can't actually run these 2 things in parallel. But I know that there's a finite number of combinations I could be in. So the goal now is simulate. By the way, does the parallel execution idea make sense? Yes? No? Okay, cool. So I want to simulate a parallel execution of a string W on two DFAs with a single DFA. That's the goal. I need to somehow simulate the parallel execution of a string on two machines with a single automata. So let's think about how we would design something like this. Without any prior knowledge of the two machines and their state spaces, I know that after reading a single character, or after reading k characters, there are 3 options for the first machine to be in, and then there's 3 options for the second machine to be in. So what if instead of running a parallel execution, I captured all possible parallel states as, how many possible combinations could I have? Where machine 1 is in state I and machine 2 is in state j. So assuming you know nothing about the two machines, oh yeah, go ahead. 9, right? So again, I know nothing about the DFAs. All I know is that they each have 3 states. I could be at any arbitrary state in this one and any arbitrary state in this one at the same time. There's 9 possibilities. So let's mimic that. I'm going to call this, these are ABC, that's 0, 1, 2. And it actually might be less than 9 because 9 would respect the ordering of the states, right? So I think it would be 6 because you would have to eliminate the double counting of the 2 states. So 3 of them will, so the states that will be overcounted are the ones that, for example, if I were to capture the parallel position of Q0 and QA, that's the same as capturing QA, Q0. So I don't want to double count it. So let's capture all possible pairs. Okay. Another way of phrasing this problem is that we have some A here and some B here, and A belongs to the set of states from Q1, and then B belongs to the set of states, Q1, and then B belongs to the set of states from Q2. That reduces my countability. So if we were to start drawing this out, Q0, QA, help me out here. Q0, QB, Q0, QC. What else do I have? Q1, QABC. Did I? Q1, QA, Q1, QB. Maybe I do have 9. Q1, QC. Nothing's been duplicated so far, right? And then, what do I have? I have Q2, Q1. Here's where my duplicates, I think, come in. Q2, Q1 is a duplicate of Q1, QA. So this is a duplicate. Is it? Hold on. No, it's not. Okay. Q2, QA. QA. Q2, QB. And then what do we have? We have Q2, QC. Okay, now, I guess you were right about 9. I don't have duplicates in here, right? It doesn't matter. So I draw all of these states. Okay, so how in the world do I define transition functions? Well, I know that this machine starts at Q0, and I know that this machine starts at QA. So I'm going to draw a start state here. Okay. Now, luckily, let's say I'm in state Q0, QA, and I read a 0. Let's say I'm in Q0, so delta of Q0 for this machine, Q0 on reading character 0, brings me to what state? It brings me to Q1. What about here? delta of reading QA. So I'm on state QA, and then I read a 0. What state am I in now? QA. So then what composite state am I in the new machine? The state QA, Q1 concatenated with QA. So I go here and say, okay, do I have a Q1 QA? I should. That's this one. On reading a 0. So does the path of drawing transition functions make sense here? What I've done, to summarize, is I want to run the string on 2 different machines. I can't do that in parallel. So let me simulate every possible pair of transitions, or sorry, every possible state pair possibility with a state space that captures the product of the 2 individual state spaces to determine where I go next in an arbitrary way for any possible transition output. I take the next character 0, simulate it on machine 1, see where I end up. I take, and in this case, I ended up in Q1. I take the same character, simulate it on machine 2, see that I end up in QA, concatenate both of the results, and that's where I go next. Real quick, what should the accepting state be? Q2, QC. So on and so forth, you can fill in the rest of the transition function states. Does this make sense somewhat? Okay, I'm at time. Happy to take any questions at this point. Otherwise, enjoy, oh, it's not the weekend. Enjoy Thursday, I guess.